Okay, so to begin with, I have a question for you. You can see this particular piece of code on your screen. It's a pretty short piece of code and a rather simple algorithm. But can anybody tell me what is being done here? What exactly is this code doing? So you can focus only on this line, basically. That's essentially where the work is being done, these two lines. The rest are just initial conditions and rest of the stuff. The entire code is here, basically. That is, entire code of importance is here. What problem are we solving here? Can anybody tell me that? Yes? If we take a look at what I'm really doing here, you can see that what I'm doing is something like this. I'm starting with some value of Q and some value of P, and then changing them. Q changes over to Q plus P into H, and P changes into P minus Q into H, where H is some, and T of course changes to T plus H. That's what is happening at every stage. What was Q earlier becomes Q plus. I hope everybody is aware of what this thing means. Anybody who has a confusion about this, please speak up. That this is something, of course, unique to Python. Not unique, but this is something you find in Python and not in other languages so often. It's called packing and unpacking. But the basic idea is the right-hand side is calculated first. That is, this part is calculated first. So given Q and current values of Q and P, you calculate Q plus PH and P minus QH. And then that actually is put in a tuple. That is, these two numbers come together as a pair. But when you say Q comma P equal to that, that gets unpacked. That is, Q becomes Q plus PH and P becomes P minus QH. So that's what is really happening in this code. And T becomes T plus H in the next line. That's what plus equal to means. So what physical problem are we solving here? Note that we are starting with the value of T, which is 0. We have a H, which is of course a time step here, 0.1.
Simple harmonic oscillator.
Exactly. What we are doing is solving the simple harmonic oscillator, basically because what we are saying is we are changing Q. And if you look at delta Q by delta T, you are changing Q by PH and delta T, of course, and changing T by H. So delta Q by delta T is P and delta P by delta T from the next equation is minus Q, which of course is a discretized version of the equations Q dot equal to P, P dot equal to minus Q, which all of you should realize are nothing but the canonical equations of motion for a Hamiltonian given by this, right? Or, as should be pretty familiar to all of you, this is really the simple harmonic oscillator without those omega m etc. factors. They have all been put equal to 1. Anybody has any questions so far? Is this clear to everybody? So no questions. Okay, fine. So this is one piece of code, which is of course nothing but the plain old Euler algorithm. That's all we are doing here, right? We are just taking the rate of change within an interval to be just the value of the derivative at the beginning of the interval. So whatever P is now, you take that to be the derivative for Q in the entire interval between T and T plus H. And whatever is the value of Q now, you use that to calculate minus Q, which becomes a derivative at the beginning of the, which is the derivative at the beginning of the interval, which becomes your approximation for the derivative throughout. This is of course well in line with whatever we have studied so far. And in fact, it's the first algorithm that we actually studied, the Euler one. Okay. But now what I will want you to take a look at is another piece of code, which is similar. In fact, it's essentially the same code, right? Except that the two lines have been broken up. Instead of writing these two lines together, what I've done is I've written this P equal to P minus QH line, then I've written the Q equal to Q plus PH line. Okay? Clear? So, firstly, my question to you is, are these two codes identical?
No, sir.
The previous one and this one? Yes? Sorry, I couldn't hear you.
No, sir.
Why not?
Because in this case, first P is being calculated, then that P is calculated for the Q.
That P is being used to calculate the Q. Right. So if I were to actually write this thing out properly, let's say the ith Q in the previous code in Euler, what we were doing is you're calculating the I plus 1th Q using the ith Q. Of course, it's the ith Q which you use anyway. And you were using the Pi delta T for that. And Pi plus 1 is Pi minus Qi delta T. That was the actual algorithm that was being used. Despite the fact that the variable, if you look at the name of the variable, they were still being called P and Q on both sides of the equation. What this really means is the earlier PQ were used to calculate the right-hand side, and that went into to calculate the new P. This, of course, was the situation for the previous code, that is for Euler. For this one, for the second version, what we did was we calculated the Pi first using this. But when I calculated Qi plus 1, I calculated it using a code which looked very similar. You just wrote Q plus P into H. But the P now has already changed. So it's plus Pi plus 1 delta T. So these two algorithms are different, right? And of course, if delta T were really infinitesimally small, it would make no difference whatsoever. They would be exactly the same algorithm. But delta T is not exactly not infinitesimal. In fact, I've deliberately chosen a rather big value, large value for delta T of 0.1, just to illustrate what's going to go on when you did these two, when you use these two pieces of code. But now, before I go any further, which one do you think would do a better job? The first one, the Euler, or this one? Yes? I'm just asking you to guess. So, any guesses? Which one is better? By the way, such a question usually means very little, because when you say which one is better, you should usually take a look at what kind of thing are you looking for. Some algorithms may be better at something, some algorithms may be better at something else. But what is your gut feeling? The first one, in which you use the same derivative the same place, and the second one where you mix up the derivatives. Which one do you think would be better? I'm just asking for an opinion. Unfortunately, I've not learned how to set up a poll here yet. I should learn that. But somebody can just say which one is better, 1 or 2. This is 2. The previous one was 1. So Gaurav is saying second. Well, is Gaurav allowed to answer?
Hello, sir.
Bye.
Second on, sir. Second on, sir.
Hello? Sorry, I couldn't hear you.
Second on.
So Amlan Datta is saying no, I guess, to Gaurav being able to answer, right? He is not allowed. No, he is allowed, of course. But anyway, I would have loved to hear the students first rather than the TAs. And I think some of you have. Sharon has said first. That's the only one who has written something. Somebody else said something, I couldn't catch that. Okay, one thing, when you are unmuting yourself, just unmute, wait for a while, wait for a second, and then say. Because sometimes your microphone takes some time to catch up. So if you just unmute and speak, what very well often happens is that what you're saying is not audible. I have at least one committed answer from a student, which is the first one. And Sharon, could you say why you think it is the first one and not the second? Any reason, or is just a gut feeling? Gut feeling is fine.
Because in the original equations, we are taking the derivative at the same time. I mean...
Okay, you are saying that when you wrote down the equations themselves, Q dot and P dot, where of course both of these are approximations to the correct answer, right? Your feeling is the first one would be a better approximation because it reflects the original equation's intent, so to speak, right? Because the original equation really
Yes,
was
sir.
P dot equal to minus Q and Q dot equal to P, where Q and P were at that given instant. By the way, this is not the end. What we have done here is this one. The second code is not the endpoint method, right? We have already studied the endpoint method earlier, which is you're taking the derivative at the beginning, you take the derivative at the end. Of course, to take the derivative at the end, you either have to solve for y because that becomes an explicit equation, or what you might do is you might want to what do you call it? Well, you want to predict the value of y at the end, then use the predicted value of y to calculate the derivative there, which is essentially what we have done in all the Runge-Kutta-like algorithms so far. But let me just see whether what you think is actually working out here. Let's try running the programs. So this one of them was called Euler.py, and its output goes in the file called Euler.dat. I hope I remember that right. And the other one was called Euler_simp. Okay, so I've run the two programs to see what the output looks like. Okay, let's.
So the first one probably will give some damping.
Okay. So you are actually changing your answer now, right?
Yes, sir. Yes, sir.
Okay, good. Let's see. So notice this is what the Euler algorithm predicts. Can everybody see the line? Or maybe I will. So this is the prediction of the Euler algorithm over a long time. Okay. So of course this is just a harmonic oscillator. We started out with 1 for Q and 0 for P, and you expect the output to keep on oscillating within +1 and -1. And if you look at the first part of this, say for the first up to t equal to 10, for example, it sort of looks oscillatory, but even there you can see that it's growing, right? And it's growing rather rapidly. And in the end, when you plot the whole thing, you see this is what is coming out. Okay. So this, of course, is bad for the long run predictions. Now you might say, okay, fine, this was just an Euler algorithm. That too for an H value of 0.1, which is rather large. Now I must confess that I've used a large value of h just to illustrate this problem more dramatically. If I use a smaller value of h, this problem would still be there, but it would be not so obvious. Okay, but is my other argument at all doing any better? Other code, so that I think was in Euler.sim.dat, and the same code I'm plotting t versus x here again. And this really seems to be doing much better, right? A nice oscillatory behavior between +1 and -1. And of course, there's not an exact sinusoid. It can't be because we are doing numerical calculations, but it's not too bad. I would definitely argue that this is pretty close to what things should be like, right? Is it okay? Now, just to show this in more dramatic detail, let me just plot the phase space curve. Phase space meaning P versus Q. Here, of course, we plotted time, Q, and P in that order. So if you were to plot using 2:3, what I will get is a phase space plot, P versus Q, or Q versus P, doesn't really matter, for the output from this second code. And this is what it looks like. Okay, what curve is this, by the way? Not exactly, of course, but what curve does this approximate? Yes?
Ellipse.
Well, it looks like an ellipse, but it's actually a circle. At least in this unit it is, right? It looks like a circle ellipse simply because GNU plot automatically uses this, what do you call, the golden ratio rectangle to plot. So it's really using two different scales on the two axes. Okay. If I had, instead of doing this, if I had just used set size square and then plotted it, then it looks like what it really looks like in this piece of code. Okay. No, okay, of course, saying that this is a circle rather than an ellipse is rather meaningless because P and Q are dimensional quantities with usually different dimensions. But since we are stuck with dimensionless P and Q here, we can compare their sizes and say that they are equal on both axes. But doesn't, okay, that's really, anyway, why is this an ellipse or a circle? What should the graph really be? What is the exact graph for this problem? For this problem, Q dot equal to P, P dot equal to minus Q. A graph between P and Q, what should it show up as? I'm asking for the exact solution.
So it should be a circle.
It should be a circle because energy conservation, right? This has to be equal to constant as time evolves. So P square plus Q square is a circle whose radius is square root of twice the energy. So this closed curve nature that you see sort of tells you that energy should be conserved in the motion. Now, strictly speaking, this curve really is not an exact circle. If I were to look at it very carefully, I would see that there is a deviation between this curve and the circle. I'm not sure whether it can be picked up at this scale, so I'm not even going to try. It may not be possible to show up the difference at the scale in the graph itself, but there is a difference. Okay, to see the difference, the easiest thing would be to, instead of plotting this, let's just plot p square plus versus q square as a function of time. You understand that? That's what we are trying to do, because that's, of course, a conserved quantity. So if it were really a constant, it should come out as a straight line. But let's see what it comes out as. Q is the second column, so that's $2 squared plus $3, squared, with, I think with lines would be essential here. So note, this is the energy curve with time. It is not a constant. It is oscillating, right? But if you look at the oscillations are really over a rather small range. It's a rather small oscillation. It looks like a huge oscillation in the graph right now. But if I were to, say, plot using putting a y range, say, just to put this in context and see the whole thing in scale, this is the actual value of the energy, and this should be sort of fixed here, and it's going up and down like this. Okay, so it's a rather small narrow oscillation. Let's just contrast this with what you had in the first algorithm. So instead of the phase-based plot, again, instead of using the second program, if I just use plain Euler output, this is what the output looks like. And you should all appreciate what's happening is starting out in a rather small circle, but the circle keeps on expanding. Why? Because Euler algorithm does not care about energy conservation. Neither, by the way, does a second algorithm. It doesn't give you a conserved energy, but it conserves energy on average. Here what's happening is the energy is not conserved at all. It keeps on spiraling outwards. Just hold on. Okay, so now I would have liked to spend a whole class on this, but I simply can't because I have to make a start on the second topic. But this is basically an illustration of the difference between two different kinds of algorithms. So let me just point out that if we had to look at the Euler algorithm, let's give the second one a name. It's called the symplectic algorithm. Symplectic algorithm, there's a whole class of symplectic algorithms, and the theory behind them is really rather fascinating. And I would have loved to talk much more about it, but I simply don't have the time to. But I'm pretty sure somebody else will also talk about symplectic algorithms later on. But one important point here is, for the harmonic oscillator, the situation is simple enough so that you can actually do an explicit calculation and see what's coming out. Look, what's happening here? Qi plus 1 equals Qi plus Pi delta T, and Pi, right? So that essentially means that you can write this as Qi plus 1, Pi plus 1, the new matrices. I need a bit of space, so. I can write this in the matrix form, right? And the matrix formulation would be anyway, for lack of time, I'm not going to go through the whole thing, but maybe let me just make make a simpler statement without going into matrices and all that. The conserved quantity Qi plus 1, if we were to square it, and of course Qi plus 1 square is not the conserved quantity, but in theory this should be a conserved quantity, right? But if we were to square both sides and add, Can you see what's going to come out? What does this equation tell you? To square and add these two sides? Yes? Is it going to come out to be the same? Of course, you saw it doesn't come out to be the same, right? You saw the amplitude keep on going up. That means the energy is increasing because of the algorithm. But here you can explicitly find out what it is. To square and add the two, what are you going to get? Sorry, I couldn't hear you again.
So 1 plus h squared.
Yeah, so it's going to be 1 plus delta t whole square times this whole thing. The cross term between qi pi will cancel out. But notice what is happening here. What's happening here is energy in the I plus 1th level becomes energy in the ith level into 1 plus delta t whole square. Sorry, not 1 plus delta t whole square, but 1 plus delta t square. So notice that delta t is of course pretty small in most calculations. I have deliberately taken a delta t which is large. So 1 plus delta t whole square becomes 1.01. However, no matter how small delta t you choose, this number is bigger than 1 and the energy gets multiplied by the same number bigger than 1 at each stage. What that means is it does not matter how small your delta t is. If you continue this for a long enough time, this energy will always grow exponentially. A smaller delta t will make the exponential growth slower, but it will still be exponential growth. So given enough time, it's going to blow up. Okay? So that is going to happen for this. I will urge you to try calculating what happens for this one and see whether you can understand why the energy does not blow up, but rather oscillates. Okay? That's something which I'm leaving you as a mathematical exercise to verify. Why can you understand the oscillatory behavior of the energy? Of course, it would be great if I could find out that for this algorithm, qi plus 1 whole square plus pi plus 1 whole square is exactly equal to qi square plus pi square. Then, of course, there will be no change whatsoever. It's not that. It's a bit more complicated than that. But I would like you to try to figure out why this thing is going to keep on oscillating. Okay? So this is slightly more, it takes slightly more work than this one. But here you can easily see why the Euler algorithm is running out of the way and this one isn't. Symplectic algorithms basically have this advantage that they preserve something called the symplectic structure of the canonical equations of motion. So have you been taught about that in your classical mechanics course? Yes? No? Maybe? Have you heard the name symplectic before? No. Okay. So that's very possible. After all, symplectic algorithms is a bit too symplectic is a special kind of geometric structure that the canonical equations of motion have. Okay, so what I will do is I will sort of leave this as a teaser right now. I will give you some problems to solve using symplectic algorithms in the worksheet so that you can get you can of course implement this algorithm without even knowing whether that is a symplectic algorithm. So I will give you some examples of those and try to see whether you can figure out what's good about those. If I get time at the end of Tuesday's class, which is unlikely, I will try to explain to you exactly why what is a symplectic algorithm and why it does better at certain things. By the way, you might think that instead of using Euler, I could just as well use RK4. That's more accurate. Of course it is. For a same value of step size, RK4 has a much smaller error. However, this energy non-conservation, more importantly, this so-called secular growth of energy, a growth independent of, not an oscillatory growth, but a growth which keeps on progressively accumulating. That happens for the RK4 as well. So if your focus is on energy conservation, and very often it is, suppose you want to do a molecular dynamic simulation of a large number of molecules, then because of the number of collisions and interactions and so on, if you don't use an algorithm which tries to conserve energy, even your best algorithms are, say, if you use RK4 for example, firstly, using RK4 when you have lots and lots of molecules interacting with each other is a horribly complicated task, but much more importantly than that, it's actually going to play havoc with energy conservation very soon. It will not even have to wait for a long time. So you want to simulate a statistical mechanical system using molecular dynamics, which is part of your course later on, you would not really sort of rely on this kind, on the Euler or its subsequent algorithms. You would actually try to rely more on symplectic algorithms. The symplectic algorithms are specifically ones which are best suited for solving the canonical equation of motion type of equations. That is, q dot equal to del h del p and p dot equal to minus del h del q. I will not talk about this any longer today, simply because I have to talk about something which is a much bigger topic. But if I find time later, I will come back and talk to you about why the symplectic algorithms are better. Better at some things. I'm not saying they're better at everything. Depending on what you want to look at, the symplectic algorithm may outperform other algorithms. But they're also limited. The symplectic algorithms only make sense if your original equations have a symplectic structure, which essentially means, okay, let me just tell you what the symplectic structure thing is, at least. I owe you that much. Okay, let's just say, all of you know this, right? Q dot is del h del p. P dot is minus del h del q. This, of course, is not one equation, but 2n equations, right? If n is your number of degrees of freedom, you have 2n equations like this. I'm not using fully differential geometric language here. I'm just saying q1, q2, q3, p1, p2, p3 with no other connotation here. So basically, you can write this set of equations as a matrix equation, which looks like this. Let's say, let's take a matrix X, which is a phase-space matrix, which is made out of Q1, Qn, P1, Pn. So a 2n by 1 column matrix, 2n rows and 1 column, with all the Q's put in first, all the P's put in after that. So the equations can be sort of written. It would be nice if you could write them like this: grad H. That is, where grad, of course, is gradient with respect to Q's and P's, with respect to these X's. But can I write this x dot equal to grad H? Can I write x dot equal to grad H? Yes? Well, it's not just signs won't match. More importantly, even the elements won't match. Right? X dot equal to grad H would have meant Q1 dot is del H del Q1. Right? That, of course, is not the case. You want Q dot not to be grad H, but that is not Q1 dot not to be del H del Q1, but you want Q1 dot to be del H del P1. Okay. So what you want is a set of equations which look like this: Q1 dot Q2 dot Pn dot del H del Qn, right? With a minus sign here. And minus sign for all the P dots. But you should realize that you can get that by starting with del H del Qi's, the right order. But somehow I want to ensure that the lower block moves up and sits here, and the upper block shifts down with a minus sign. So can you think of how to do that? how to take a column vector. Suppose I have a column vector like 1, 2, 3, 4. I want to do something to it, multiply by some matrix so that it becomes -1, -2, and 3, 4. The lower pair moves up and the upper pair goes down with the minus sign. How would I do that? What kind of matrix would I put in here?
So the eta matrix, it's 0, identity minus identity 0.
No, identity?
0, identity minus identity 0.
Yeah, it's not called the identity matrix, but basically, yeah. It's not called the eta anyway, it's called something else. So basically what you can write here is x dot is a matrix J times grad H. Okay. And it's this matrix J, which is a block antisymmetric matrix. And it is an antisymmetric matrix, which actually helps us to give rise to a new kind of structure which these equations have. So, okay, let's not waste too much time today on this because I have to start on the second topic. But I will come back to you, and I hope all of you understand this, that if you put in a matrix like this, which is where the 0, of course, is an n by n 0 matrix, so that when you multiply this by this, the 0 takes care of this, kills it completely. The identity makes this move to the top. On the other hand, when you multiply the second row, minus identity takes this, pushes it down here with negative sign. And of course, the del H del P's just vanish because they are multiplied by 0. So this is the compact way of writing this structure. There's the Hamilton equations of motion. And this gives rise to certain quantities staying invariant. And that is where the symplectic structure comes from. Okay, too much detail to go through right now. So I will just stop here about this particular topic. If I have time, I will later on come back and explain to you why symplectic algorithms work better. But I will give you a couple of symplectic algorithms to work with in the worksheets so that at least you can implement them and see whether you can figure out what kind of improvement they make. Okay, so that will be sort of an experimental introduction to symplectic algorithms, so to speak. Okay, so let's stop this now and let's go on to the actual major topic that I have to cover in the next 1 and 1/4 class, which I think is pretty much of a tall order. So this is how to implement partial differential equations on a computer. Can everybody see this? My slides on the screen?
Yes.
Yes, sir.
Okay. So I'm not going to talk about all possible partial differential equations. That would have taken a whole semester to cover anyway. So I will just take a very special example. This is the heat equation in 1D. I hope everybody knows what the heat equation is, right? Del U del T is the conductivity times del 2U del X2. Right? That would be the heat equation if there was no external source, but if you have an external source, it could have a value of Qx of T. So this is a differential equation which can describe, among other things, that variation of temperature on a rod which is being heated up from outside and so on. I hope all of you are familiar with this equation. Yes? No? What? Sorry, if anybody is trying to type, please don't. I can't see that.
Yes, sir. Hello? Yes, sir.
Okay, fine. Now, I'm saying this is an IBVP. That is an initial and boundary value problem. So this is the difference between partial differential equations and ordinary differential equations. To get a complete solution, giving the initial condition is not enough. You also have to say what will happen exactly at the boundary of the problem. This being a one-dimensional problem, it's really rather easy to state what's going to happen. You need an initial condition, that is, this is a time evolution equation for u, and you need to tell me what is the value of u at t equal to 0. So you you have to be given an initial distribution of temperatures. Okay, ux0 equals f of x. I'm just going to say temperature just because it makes me feel more comfortable to talk about a physical quantity. But it's just any quantity which obeys this equation. By the way, this equation should be of great interest for the other course I'm teaching in your class. Can anybody tell me why? Why should it be of great interest in quantum mechanics?
The Schrodinger equation in position basis also have the same form.
Yeah, this is exactly the Schrodinger equation, except that Schrodinger equation would have IH cross del psi del t. Of course, I can move the IH cross to the other side. But that would mean that it would require an imaginary or at least complex coefficients here. But in fact, the algorithms that we use to handle the heat equation can also be used with very little change to understand how a wave function will evolve with time. So in quantum mechanics, we use this all the time. And we also need to specify the boundary conditions, which is what is happening at the edge at x equal to 0 for all times, and at some other x where the other edge is, let's say at x equal to c at all times. And you could have complicated boundary conditions. For example, you could have a boundary condition which says, you could have something as simple as saying u0 of t is 0, right? That's just saying that the temperature at one end is always 0. You could have a condition which says uc of t is just 1. So temperatures at two ends are fixed for all time. That's possible. The temperatures at the two ends could be things which change with time. If you have a rod which you are heating up at one end, at both ends at different rates, and I try to ask what will the temperature distribution be throughout, you could have something like that. And not only that, it's not only the value of the derivative, also the value of the u, also is spatial derivative is something which may go into the boundary condition. Is it okay? So this is a general boundary condition. In most problems, your boundary conditions will be simpler. They will usually involve either u or the derivative of u. Usually not both, but sometimes they may. And it may, of course, it's possible that at one end of the rod, the derivative is given. The other in the rod, the u is given. By the way, derivative of u, del t del x essentially gives you the rate at which heat is flowing in. So this is really physical. You may have a constant rate of heat flow at one end and some variable temperature or some other constant temperature at the other end. So you may be in possession of the knowledge about what ux is at one end and what u is at the other end. So a boundary condition might very well be mixed. But these are always at the end of your spatial coordinate. And the time evolution, of course, is governed by this equation, subject to the initial condition that at t equal to 0 is going to be like this. And at all t, the boundary conditions are going to be obeyed. Okay. Now the question is, how do we solve these equations or equations like these using numerical methods? And that is a lot more difficult than solving ODEs in general, and which is one of the reasons why you don't really try to go in for very high-end algorithms here. You essentially use simple algorithms with perhaps small time steps so that it sort of can be kept in check. So we will simplify our discussion simply by saying let's take qxt equal to 0 so that it just becomes the homogeneous heat equation. Del u del t is k del 2u del x2. Okay. And what we want to do is want to find out, ideally, u at all x and all t. But as you all know, that's impossible simply because all x and all t would be way too many points to really cover. So what you do is you first start with discretizing space-time, not in reality, but for your numerical calculations. So what you say is something like this. instead of trying to find out u at all x and all t, you will be satisfied with u at x0 plus I delta x. That is, you have broken up your spatial coordinate into delta x size chunks and your time coordinate into delta t size chunks. So I and n, the two, okay, this is not a power. This is just a notation. I'm deliberately putting the time index up and the space index down just to distinguish between the two. The time index is up here, u and I. That means the nth time interval within that at the ith spatial position. Is it okay with everybody? This notation is going to be critical to understanding what's going to go on. It's a simple notation, but we have already used this before. We had used yn for the nth, for y at the nth time step. But here you have two things to worry about, x and t, and that's why you have two indices. And what we will do is we will essentially use the simplest possible algorithms, really. So we will use finite difference approximations for the partial derivatives which go into the equation. So you need a del u del t at xi and tn. Okay. Easy. You know this is the definition of del u del t, right? You keep xi the same in both terms, change tn by delta t, find out how much u changes, and then divide by delta t, and finally take the limit as delta t goes to 0. And it's of course this final step of taking the limit as delta t going to 0, which you cannot use on a computer, that is on a numerical algorithm. So what you are doing is you're approximating this just by saying this thing, of course, is can be approximated not by t at a infinitesimally close time after tn. I'm going to approximate this with the next time step value. So u xi tn plus 1, that is ui upper n plus 1 minus ui at n divided by delta t. And very similarly, if you want, okay, somebody please tell me this. This is ut at in, xi and tn. That's ui n plus 1 minus ui n by delta t. What would ux be? The derivative with respect to x. What would that be in similar notation? I just want to make out whether everybody has understood this notation and its consequence from there.
uni plus 1 minus uni by delta x.
Exactly. So basically here what's happening is, in what I've written down a while ago, what was happening is, since t is changing, the m index, the upper index is changing by 1, and of course you have to divide by the change in t. On the other hand, for ux is x which is changing, so the lower index I will change to I plus 1 minus un. So this of course is simply forward difference formula, which is not a very accurate approximation. So to get it to come close to the actual answer, what you need to do is use rather small steps, which is a bit of a problem, as you will discover. Okay. Of course, you could say that we could try to improve upon these approximations by doing things like central difference or higher order numerical derivative calculations. I don't remember. Did I talk about numerical derivatives in the course, in the last semester's course or last year's course? Forward derivatives, backward derivatives, central derivatives, and stuff like that. Yes or no?
Yes.
Okay, good. I did, but you may have forgotten. But in principle, the basic idea is this is, of course, a very simple-minded derivative approximation. You can improve upon this, but the improvements are more complicated, and they make partial differential equation implementations even more difficult. So we will stick with this for the time being. It's small modifications. Of course, we need uxx. And I don't know whether anybody remembers this, but the second derivative can be approximated by this quantity. This is a spatial derivative, so you find the u at to the left, find the u to the right. That's at I minus 1 and I plus 1, add the two together, separate double the value of u here, and that gives you a good approximation to the second derivative when you divide that by delta x square. I hope everybody remembers. This is just a simple application of the Taylor series to get this as an approximate value for the second derivative. Of course, depending on your differential equation, you may need to go for higher and higher derivatives. So you may need to go in for more and more complicated terms like these. So what does the equation del u del t equal to k del 2u del x2 become? It simply becomes this, right? On this side, this is del u del t. This is what? Del 2u del x2. So you just plug that in. These are of course the left hand side and the right hand side contains things which are approximations to del u del t and del 2u del x2. Okay, right? So is this clear to everybody? I'm assuming from the silence that it is. Fine. So note that we are solving an initial value problem, which means that I know at I equal to 0, at n equal to 0, I know all the u's at every I. So at n equal to 0, at every x, the ux comma 0 equal to fx, that initial condition, can be translated to the knowledge of u0i for all I. So I know the initial value completely. But then notice that if I know that, if I plug it in this equation, that will tell me u1i, I'm reading the n index first, u1i for every I. Is that okay? Is that the correct thing to say? Since I know u0i for every I, that's the initial condition, I can use this to calculate u1i for every I. Is everybody okay with this? Everybody, is there any can you not see any problem?
So second order equation needs at least two boundary conditions.
No, there's no second order. In time is first order. No problem at all. That's why just knowing the initial value is fine. There's something else which you will need to worry about. Can anybody tell me what you have to worry about? Look at the right hand side. Can I calculate the right hand side for all values of I? I need all values of I, right? That is all x points. Not all x points, but I've discretized my x into a bunch of points. I want u at all those points at a later time t. Can I find that out just from the right hand side of the equation? Yes, no, what? So, okay, what are the I values that I have? I starts at 0, goes up to some capital N. 0, 1, 2, 3, 4, up to some capital N. Can I find out u0 n plus 1 from here? u1 0 from here, from this equation? Or u1 n from this, 1 capital N from this equation? To find out u1 0 from this equation, what you need is the value of u0 0, which you do know. And what do you need to calculate the right hand side? u01, which you know, minus twice u00, which you also know, plus u0 minus 1, which makes no sense whatsoever. Is that okay? Do you understand that you cannot make out u0 minus 1 because there is no u0 minus 1. At equal to 0, you have the u values for I going from 0 all the way to capital N, or maybe capital N minus 1 if you have capital N points. You don't have anything beyond that. So right at the boundary, this algorithm will fail. Everywhere else, no problem. Which is why you also need boundary values boundary value specifications to say what happens at the boundary. This will work for all points in between. This will not work at I equal to 0 and I equal to n minus 1. Those are the 2 points. It simply won't work because you cannot calculate the right hand side for those points using this equation. But I don't have to worry about that because the boundary values will take care of that. So from 1 to n minus 1, suppose I am using 0 to n are known. So from 1 to n minus 1, I can use this. Simply, okay, I said from 0 to 1, but I could keep on going from t equal to 0 to t equal to 1 to t equal to 2 to t equal to 3 and so on. That is 3 delta t, 4 delta t and so on. And this would work fine. Okay. Is that okay with everybody? Except that the boundary conditions have to be specified like this. Okay, I will leave the slides up so that you can read the slides and find out. I just don't have the time to go through the full details of this. But I'm pretty sure it should be pretty easy for you to figure out what is going on here. This is just a a1 u at the end plus a2 derivative of u at the end, the boundary condition which I'm putting in here. The extreme values, that is at the two ends, cannot be found from the differential equation itself, or even the discretized version. Have to be found from the boundary conditions. And that's easy. The extreme points are the boundary points. That's why you need boundary specifications. Okay, having said that, let me point out that you could also do it somewhere else, some other way. Remember earlier we talked about implicit versus explicit methods, right? This is what kind of method is this? Explicit or implicit? The difference is in the explicit method, you have a formula for calculating the value of u at the next time step. Do you have that? Yes? Remember, your values are given at t equal to 0. And you want to find it at t equal to 1. Can you find that out by just plugging in the values in this formula? Or do you need to solve anything? From n equal to 0 to n equal to 1, do you need to solve an equation for that, or is this just a formula for that?
This is an explicit formula, so we don't need to solve.
It's a formula, right? Don't need to solve anything. You just move this to the other side. It's done. In fact, this is the formula. So that this is an explicit form. But you could get an implicit form just by saying that instead of using the derivatives at the beginning of the time interval, which is what is being used here, the values of these quantities at the beginning of the interval, if I had used instead the values at the end. Okay. So to find the change, uin plus 1 minus uin, instead of using the values at the beginning, I'm using the values at the end. So that is why I'm just using the n plus 1s. Yeah. That of course is more complicated because you have to solve a bunch of equations for this. But can anybody guess what the advantage will be for this? You should know that because you've already seen that in the last class. Last bit when we talked about implicit versus explicit. Both of these, of course, are approximations to the actual answer, but this one has an advantage.
More stable solutions.
These give you more stable solutions. Right. We will explore that in detail in the next class. Why one is unstable, or why one is the first one is conditionally stable. That is stable only for certain values of the delta t delta x's. This one actually is unconditionally stable. More complicated, you have to solve an equation, but you don't run the risk of your problem giving you completely wrong answers because of instabilities. So we will explore these things in the worksheets a bit. And okay, let's skip that and let's come to the final point. That is, this of course was the original implicit formulation. Sorry, explicit formulation. That is, given that values now, find out the values later just by using a formula. And this one, where I've just changed this, all these spatial derivatives I've calculated at n plus 1. This is the second one that we talked about. This is the implicit formulation, the more complicated one. Now, in fact, a compromise between the two happens to be something which is both unconditionally stable and more accurate. Can you tell me what you would use instead of using either of the two? What do you think would give you more accuracy, other than this one or this one? Something simple that you can do, given these two, given that both of these give you good approximations, decent approximations. How would you modify the algorithm to get to something which is perhaps a better approximation? This one, remember, essentially calculates the time derivative at the beginning, right? At t equal to
Take an
n,
average.
I'm calculating the derivative by, yeah? Yes?
Take an average.
Sorry, again, take an average. Exactly. This is the value at the beginning, this is the value at the end. If you take the average of the two, we just add the two together and halve it, which of course is still an implicit formalism. So you have to solve for UIs, UI n plus 1s. But what you have is an advantage that this becomes a more accurate algorithm as well as a stable algorithm. This also happens to be unconditionally stable. That is stable for all values of delta t and delta x. Okay. So if you were to sort of try to simulate the Schrodinger equation, for example, time evolution of a wave packet, by using this algorithm, it turns out that unless you use a very, very tiny delta t, and where of course you run the risk of random errors or round of errors, more importantly, this original algorithm would hardly ever work. The last one would work rather nicely. It will be accurate, it will also be stable.
Sir?
And this is called the Crank-Nicholson algorithm. Okay, yeah. Go ahead.
So instead of taking the average, can we also use predictor corrector method or something like that?
You could use something like that, except that all of those will only add to the complications. Note that for ODEs, you have only one U, right? So from one U, you are predicting the next U. Here you have actually capital N U's, where capital N is a rather huge number. That is, for each small n times, for each time step small n, you need UN0, UN1, UN2, UN3 up to UN capital N. So quite a lot of UNs. And for a good calculation, these capital N will run in thousands. So anything more complicated would be, well, horribly difficult to handle, let's say. You could, of course, improve upon this, but frankly, the Crank-Nicholson algorithm is good enough for most purposes. Although, of course, let me point out one thing. Just because it's stable for all values of delta t and delta x, you're not going to use arbitrary values of delta t and delta x. You want accuracy. For that, delta t, delta x would have to be small. The good thing is Crank-Nicholson can be accurate even for larger values of delta t than, say, the first one or the second one. That's simply because it has a smaller error. Okay, so these are the three basic algorithms that we will use to solve the heat equation. But before I go there, I need to ask you one thing. You have not been taught how to solve linear simultaneous equations yet, right? Using NumPy or other methods? Yes or no?
No, sir.
Do you realize why I am talking about solving linear simultaneous equations? This equation that you have to solve, ui n plus 1, is actually not only, you don't only have ui n plus 1 here, you have ui n plus 1, I plus 1, un plus 1, I minus 1 also. So it's really a set of simultaneous equations you have to solve, not just one equation. That is the basic difference between doing an ODE and doing a PDE. So you would have to solve simultaneous equations. I will just give a quick hint on that in the worksheet itself. You will learn that in more detail in the next part of the course when Ananda takes over. The other Ananda, that is, on the AMG. He will talk about matrix algorithms, but I will just give you the basic code to find that out, how to solve this. Using NumPy is trivial. Unfortunately, if you're using Fortran, the only way to do this is the wrong. Not the only way. Fortran also has nice packages, except that I don't know anything about those packages to solve simultaneous equations and stuff like that. Okay, I think I've overshot my time. So if there are any pressing questions, please ask now. Next day, we are going to take a detailed look at the theory behind these algorithms, at least try to explain why this is unstable. Hopefully you will see that this is unstable in the worksheet itself by looking at an example. But next day, I will try to explain why it is. Mathematically, how would you figure out that this is unstable and the other two are stable? Okay. So any questions? If not, let's stop the class. Yeah.
Hello, sir. I have a question regarding the current worksheet.
Yeah. Go ahead.
Yeah. So, sir, in the implicit Euler algorithm, so do we have to solve the implicit equation by like for the specific equation that we have given, or like we have to write an algorithm to solve any general equation?
Well, that is a question about what will be considered a good answer, right? Ideally, it should be something which solves the general equation. But look, this is really, we are not really doing production level programming here, right? We are trying to learn how to do things. So if you want to push it to that level, fine. But if you don't, you just want the solution of this equation, it's okay, I guess. As long as you understand that when you actually want to solve a general equation, you would have to write a equation solver to get there. It's fine with me.
So can I use like fsolve or root to solve the implicit equation?
Anything, as long as you look, when you write your code, put in comments.
Okay.
And in the comments, you have to explicitly write, okay, to solve this equation, I use this.
Okay, sir.
So
thank you.
We know that you understand what you're doing. That's okay. Our aim is not to make a, say, production level program right now. You may be able to develop it into a program which will be something you can sort of even publish on the net. But right now, it's more about learning the thing. Okay, anyway, bye for now.